Okay, good. Welcome everyone to this public lecture that will be delivered by Professor Gerry Gilmore. I'll just quickly introduce him. Professor Gerry Gilmore is from New Zealand. He grew up in a small farm, attended Canterbury University in Christchurch, where he obtained his the first astronomy PhD in New Zealand. Following 5 years at Royal Observatory in Edinburgh, he moved to the Institute of Astronomy in Cambridge in 1984. I was only a year old at that time. Initially as a holder of SERC Advanced Research Fellowship, he subsequently had a fellowship with Royal Society Smithsonian Fellowship. He joined the faculty, becoming a professor of experimental philosophy. Among many awards, he became a fellow of the Royal Astronomical Society in 2013. His academic work focuses on the Milky Way galaxy, which is our home galaxy, and its content is evolution, which you will hear about today. He has made significant discoveries, including that of the Milky Way thick disk. The thick disk in the Milky Way was discovered by him, and an evidence of early galaxy major history. So he also works on Sagittarius dwarf systems. Professor Gilmore whose full title is, well, he has a lot of acronyms to his name. He's a fellow of Institute of Physics. There are a couple of the acronyms I don't know. Honorary fellowship with FROAS in New Zealand. Lots of it. He is an emeritus professor of experimental philosophy at the Institute of Astronomy at Cambridge University, and has an honorary fellowship at the Institute of Astrophysics in Greece. And it is my honor to welcome him to deliver this public talk. Professor Gilmore, please.
Thank you, James. It's a pleasure to be here. Given we're in the Southern Hemisphere from which I come, Tina koto, Tina koto, Tina koto. Now, I will give you a quick overview of what we see on the sky and what we've learned, particularly in the last decade or so, of what it really is and what's going on. But this is the sky as seen by a satellite, but of course in the Southern Hemisphere, one sees it by eye rather dramatically, and every culture and every people that we know of has done some interpretation of the Milky Way, partly perhaps for utilitarian navigation and cultural and planting reasons, but more generally, just because it's there and you can't help noticing it, particularly in the Southern Hemisphere. And so here are some examples. The one in the middle, the big one up there, I particularly like. Actually, it hangs on the wall of my office and has done for a third of a century. And it's a very early Australian image of the Milky Way. And here are some European ones on the right. So what I'll do is go through and give you a quick introduction to how we determined the current structure and properties, broad range properties of the Milky Way. That process taken last few hundred years, introducing the people who have done it. And it's perhaps significant that today is Women's Day in South Africa, because I have made no effort at all to bias this talk, but it happens that there's a very large number of distinguished women who have worked in this subject. You'll see them appearing as we go through. But we'll start just by turning those images into a cartoon, just to set the context of where we are. And you see this side-on pancake-like structure is a cartoon model of what we think the Milky Way looks like pretty well in broad brush today. So the part labeled thin disk is the band we see by eye on the sky. That's the visual bright Milky Way. It is embedded in this property called a thick disk, discovered in the 1980s, which turns out we now know to be the original Milky Way. In its very center, there is a bulge of stars, which we call the constellation of Sagittarius. That's the center of the Milky Way, a big bright thing. And all around it, gas and particularly dark matter extended over a very large area with a small number of halo stars that turn out to have an unusual history recently discovered that I'll tell you about. And up the top right there is a cartoon. It's another cartoon, an artist's drawing of what the Milky Way probably looks like. One needs to be a bit cautious with these colored cartoon images, because people do tend to make the Milky Way the most beautiful galaxy in the universe when they get to draw it. And so it's perhaps not quite as lovely as that, but it's something like that. So now I'll just very quickly put in context our current knowledge, approximate knowledge of the history of how galaxies form in the universe. So this is a computer simulation showing from the Big Bang, or shortly after the Big Bang, how matter accumulates in the universe and turns into something that looks vaguely like the Milky Way. So you can see the sound waves of the Big Bang. The Big Bang was sound waves. The peaks of those sound waves add up and they form these filaments and structures where the mass accumulates, particularly the dark matter, and then ordinary matter, gas and such like, falls into that dark matter. And then when it's there, it forms stars, and those stars eventually turn into galaxies. So this is an approximate history of what something like our Milky Way looked like. The important thing to remember also is that list of numbers on the left-hand side in that table. These are all critical to make this model work, and they're all just put in by hand. They're observations. We have no understanding at all of why our universe is made as it is. So I'll stop that video there and move on. But the key thing from this video is that it predicts or illustrates a rather violent early history for the Milky Way being smashed about. And that was believed to be the case until about 5 years ago. And we now know that our earlier history of the Milky Way was actually much quieter than that. So there's a very great deal of learning from observation still to come to inform these computer models before they can be made more realistic. But anyway, we'll now move on to the modern view, this post-Copernican, post-Galileo view of how we discovered what the universe was like. And the first big name in this field, as in almost everything to do with gravity, is Newton, of course. There he is with this beautiful hair to die for. And underneath it is a page from what would have been the last edition of his famous book, The Principia. But this was his model of the universe. And Newton being Newton, he built what he thought was the only universe that God would have liked, which was a perfect universe, perfect as judged by Newton in his standing in for God mode. And so he built this model and used it to predict the only information he had, which was the numbers of bright stars as a function of their brightness. And this was data that dated back from ancient Greece. In ancient Greece, the brightnesses of the stars were listed in terms of magnitudes. So the brightest one was first magnitude, and so on down to fifth or sixth magnitude. And so he had these numbers. And so in typical Cambridge theorist fashion, he worked out his theory and wrote it out beautifully in Latin, as you see there, and left a space for his figures and diagrams and tables. And he did this for everything he did. And most of the time, he just put in the relevant figures or tables, and it's the basis of modern dynamical science. But when he came to his model of the galaxy, you can see what happened. It didn't work. So he did what all Cambridge theorists did and said, well, there's something wrong with the data. Can't be my model. And so did everything he could to change the data. He threw away all the faint stuff. He put in all sorts of biases and corrections. He just cheated, frankly, as much as he could get away with. Still didn't work. He then said, well, if there's nothing wrong with the data, there must be something wrong with the people who acquired the data. This is a good lesson for Cambridge theorists. It's how they work. And he deduced actually what is correct, that people's eyes and brains don't work the way that people at that time thought they did. And that therefore a star that was of fifth magnitude was not 5 times fainter than a star of the first magnitude, but was logarithmic. It was 100 times fainter. And that's true, actually. That is how our eyes and brains work. And that brilliant factor, which explains night vision and all sorts of things, was deduced by Newton while trying to show that the ancient Greeks couldn't count stars properly. But he got that bit right, even if nothing else. It still didn't work. And then some of his colleagues pointed out that even if it had worked, even under his own laws of gravity, his model would have been unstable. He would have created a collapsing or an expanding universe. Rather amusing forethought, you might think, but at the time considered outrageous. And so he gave it up and he went away and he became a banker. So 100 years later, the two people who did make the next big step were a brother-sister pair, William and Carolyn Herschel, originally from Germany, but working in England at the time. And they came up using a telescope built by Herschel and operated by Carolyn, the two of them as a team, with this model of the Milky Way, which is not bad compared to what we see today. It's interesting that it took all this effort in Europe with a telescope and star counting and so on to end up with something that does look remarkably like that. So one wonders if perhaps they might not have taken the advice of a very, very famous American philosopher, if I slightly rephrase it, and say you can actually see quite a lot if you look. But that wasn't the way that I think people were done, science was done at the time. So now we move on and say, okay, so what we want to do next is say, I can see all these stars, but where are they? How far away are they? And so I have a slightly technical point here is how do we measure how far away the stars are? And we do this in 2 ways. The most important way is through parallax. And the video on the right shows you what the sky looks like to us on Earth because we are moving. So all the stars appear to move in ellipses. And if you look at the top left figure there, you can see a cartoon of it. You take a picture of the sky in the summer, wait till the Earth goes around the other way, take a picture of the same sky in the winter, and you see the nearby star will have appeared to move compared to the background stars. And that movement is caused just by our movement. But if we know how much we're moving, we can use that to calculate where the star is. And the bottom cartoon shows you how a person, an astronomer, on a planet 25 light years away would see Earth and the sun. Or we wouldn't see Earth, but see our sun moving. And you would see it moving across the sky, and that's the proper motion across the sky. You'd see it moving in these loops, and these loops are the parallax. And so the size of those loops tells you how far away the star is. And you also see these bumps and wiggles going on, and that's caused by the fact that we have 2 massive planets, Jupiter and Saturn, which are actually pulling the sun around. And so by carefully measuring the motion of a star across the sky, you can work out where it is, how it is moving through space, and you can also learn about the dark objects around it, planets or low-mass companions or something. And so that's the dominant technique that we'll be talking about today for how we determine distances and motions of things in the Milky Way. But there's a second way of doing it, which is historically important and is still used for larger distances. So I'll just introduce that anyway. And that introduces this probably most famous woman in astronomy of the period, Henrietta Leavitt from 1908. And she realized by looking at stars in the Large Magellanic Cloud, so it's a nice southern hemisphere thing, that there was a relationship, and that's shown on the right, between the brightness of the variable stars and how long it took them to vary for the particular type of star called a Cepheid, young massive stars. And so when you know from, therefore, just by measuring how the pulsation period of a star, how bright it really is, you can tell how far away it is, just the inverse square law. And this was first applied rather interestingly just on 100 years ago, not quite yet, 101 years ago, to discover the first ever galaxy beyond the Milky Way. Now, people forget that it's only 100 years ago that we've known that the universe was bigger than our Milky Way. And so for Newton, and in fact for Einstein in the first decade of expanding universe cosmologies, it was the Milky Way that people were talking about that was expanding or contracting or whatever it was doing. So the first ever galaxy discovered beyond the Milky Way is this one, the rather underexciting name of NGC 6822. But you see, I've underlined it there. The first object definitely assigned to a region outside the galactic system. So it's only 100 years ago that our whole modern picture of the universe started to take shape. And just for interest, here are the pictures of NGC 6822. The one on the top left is Hubble's original one, with his writing identifying the various Cepheids and other things in it. The one on the right is from a few weeks ago, is from the recent, the current state-of-the-art imaging satellite called Euclid. It's mapping the universe exquisitely. And the bottom one is from the James Webb. But if you look at for those of you who are brilliant at pattern recognition and the way that all astronomers used to have to do this at telescopes in the good old days, if you look at this pattern of the bright nebulae, H2 regions across the top of Hubble's picture, you'll see the same things here across Euclid. And so this is just a modern view of exactly that same patch. You can line up everything. It's much, much harder to do that with James Webb pictures because they're in the infrared, so you're looking at totally different things. But anyway, that's an interesting historical point. It's based on southern hemisphere observations calibrated by Henrietta Leavitt just 100 years ago. So that created the first hard information about the scale of our part of the universe. And here is that picture, our current picture of what that is. Our local part of the universe is our own Milky Way with a cluster of things around it that we'll spend the rest of the talk talking about. There's good old 6822 out in the middle, stuck in between, in the middle of nowhere. And over here is the Andromeda Nebula, M31, and its cluster of companions. So we have this two big galaxies, clouds of companions around them that make up our part of the universe, and this little isolated one halfway in between. So that's the local structure of the universe that's been learned over the last 100 years. So the next thing you want to do after knowing where stars are is to discover what they are made of. And the real advance here was made again just on 100 years ago by this lady, Cecilia Payne, who was the first person to apply the new quantum mechanical radiation transfer theory, what we call the Saha equation, to determine what stars are really made of. Before that, it was always just assumed that everywhere in the universe was like the Earth. And it was known that Saturn and Jupiter were a bit odd because they are full of hydrogen and methane, but it was assumed that they were odd. And in a sort of typical bit of ethnocentric arrogance, it was assumed that we are the perfect exemplars of everything in the universe and everything must be like us. But anyway, Cecilia Payne, who had been a student in Cambridge, so down the bottom there, you'll see the annual report written by Eddington, a famous name in the trade, and he had two students that year, Cecilia Payne, Miss Payne, and Miss Douglas. So Cecilia Payne went on and became among the first women to do a PhD at Harvard and one of the first women professors at Harvard, and rewrote our history of our understanding of the universe. Ellie Vibert Douglas, the other one, became the first woman to do a PhD in astrophysics in Canada and became a very prominent Canadian astronomer. So here's a pair of young women students in Cambridge in the 1920s, where the social structure at the time made it simply completely impossible for women to stay and achieve. And so they went and became the stars in North America. There's a little aside that I've flagged there in the middle, is that Payne's work, this is her PhD, was published as this #1 in this Harvard series. It was so paradigm changing that the great names of the time said, well, we don't know what's wrong with it, but there's got to be something wrong. And so she was required to put that in. But to her prodigious credit, she said, well, I'm required to say this, but I don't think it's true. And she was right. And we now admire her brilliance as well as her courage for standing up for everything that she believed in. Now, the next thing was understanding where all the other elements came from. It's all very well saying that they're like those on Earth, but where do the ones on Earth come from? And that big advance was developed really after the Second World War, when nuclear physics was not only being developed extensively, but was becoming declassified. And so it's possible to do all the calculations. And the first step was to realize that not all stars are actually the same. There are some that are slightly different in their chemical properties. And the big advance here was made by this lady, Nancy Roman, who was one of the first to realize that there is a connection between the way stars are moving in the Milky Way and their chemistry. And so this was a big hint that there was some information available in the chemistry. And Nancy Roman, of course, later became a very prominent administrator in NASA. And there is to be a huge space telescope named after her, launched in a year or two. So she became a very, very distinguished figure in the US community. The next thing so this goes around this way in time. The next thing was this group of 4 people. Here they are pictured in the garden at Cambridge. Margaret Burbidge, Jeff Burbidge, Willie Fowler, and Fred Hoyle. And they were the people who first were able to put together all of the nuclear astrophysics, as they called it, and work out where all the elements are created and what sorts of stars and things. And so this allowed for the first time then the possibility to work backwards and say, well, if I know where how things are created and where they're created and when they're created, I can then work out the history of where they all come from when I look at them. And the first attempt to do that was these 3 guys up on the top right. So that's Olin Egan, Alan Sandage, and Donald Lyndon Bell. And they made the first attempt to actually say, well, if I look at the very, very oldest, chemically most extreme stars that I can find, I look at their characteristics of how they're moving, and I can work out how the Milky Way formed. And so they showed that it was possible to actually do real science based on the information. And this was all put together by the lady at the bottom, Beatrice Tinsley, another New Zealander, who realized that, well, galaxies aren't just things. They're a combination, the stars and the gas and the chemical elements and so on. They're all a single thing. And so she put it all together for the first time and allowed one to analyze what was going on. Sadly, she died very young of cancer. So I barely overlapped with her in my career, but we both have similar backgrounds. And we'll come back to the Tinsley way of analyzing information shortly. There's another thing that you can do, of course, and people are still inventing these new ways of doing things. So I don't want to give the impression that, this is a closed book. There's a huge amount of information still available to be done. So here's a picture of some of my collaborators using a new, or in fact, a very old methodology. The methodology is due to Charles Darwin. And there's Charles Darwin's original drawing of how evolutionary sequences might work from his diary. And these one can turn into evolutionary trees. And here is an evolutionary tree that we made for an evolution of the Milky Way, in the sense that chemical elements behave the same way as DNA. They depend on what came before them, and they change for what comes after them. And so they're an evolutionary sequence. And so here are some of my colleagues, all of them, working with, we're losing the methodology of human anthropology. So here is a sequence of skulls showing the history of man from the earliest possible in Kenya right up to relatively modern. And we can use that same methodology, and we can learn from other series. So this is the future for young people. Don't think we know the answer. The smart thing is to go out there and do it differently and do it better. But putting all this very crude, very oversimplified summary of what we know is that basically we know that all the different chemical elements, and here's the whole periodic table with Mendeleev, the originator of the idea, are created in different processes and different sorts of stars. And these different stars, actually, it's a bit more complicated than this, but there's near enough complication. There's enough complication there. These different types of stars live in different environments for different times. And so this provides the opportunity to use the mix of different chemical elements as a clock. You've got some things that are created very, very quickly after the first star forms. And so you know that's going to be there in the oldest things. Other things won't be created for billions of years, and therefore you can find that. Then you know you've got a star that formed very much later. And the principle is very simple. So the next thing, now that we've got all set up with all what we need to understand how the Milky Way formed, is get all the information. So what we need now, therefore, is a census of a reasonable fraction of the stars in our Milky Way galaxy. And that's what this is. This is actually this is not a cartoon. This is not a picture. This is a set of 2 billion individual observations put together on the sky. This is the Gaia current catalogue with the 2 Magellanic Clouds, which we'll come back to later, down here in the southern sky, and the rather dull northern sky over there. So this is the way to do it. What you need is a goddess. And the goddess we have is called Gaia. Gaia, it was in Greek mythology, the second of the gods after chaos. And she, a mother goddess, the original mother goddess, was the goddess who created everything in the universe. But being a nice mother goddess, she not only created the universe, she also created the concept of understanding. So she created the fact that it was possible to know things and understand them as well as to be part of them. And we thought this was a perfect name for a way of understanding our own Milky Way. So we have this mission, this project called Gaia. It's a satellite. The satellite itself is very simple. It's a ring with 2 telescopes hanging on it and feeding the light to a very, very large camera. The interesting thing about it, 2 interesting things. The most important interesting thing is it measures lots of different things, and we'll come back to this in a minute as well. You don't need to know what these words mean, but all of these different things are being measured by Gaia. And so there's a very, very large number of properties, different properties, independent properties of up to 2 billion objects. The other interesting thing is the accuracy numbers we're talking about. So you probably already read it. We work in units of micro arc seconds, which is means for an engineer a lot, but for a person it doesn't make much sense. And in Wikipedia, it's quoted as this: the size of what they call a period, what I would call a full stop, at the end of a sentence on the moon as seen from Earth. Now, frankly, I don't think that's helpful in the slightest, because I have no way of visualizing how far away the moon is. It's far enough away. But anyway, whoever wrote that for Wikipedia thought it was smart. The important point is it's a very, very small number. And so we're talking extreme precisions. An analogy I like slightly better is that it is the thickness of a fingernail. So not the width of your finger, but the thickness of your fingernail, as for a person sitting here in Cape Town, as measured by someone at the North Pole, if you could imagine the curvature of the Earth getting out of the way. So it's the thickness of a fingernail across the Earth. And these are the sort of routine accuracies that we're talking about. The numbers are impressive. The other important thing is how long these projects take. So you can see over here, I started working on this. It's a very important lesson for everybody is if you're going to work on a big project, start young, because it'll take you the rest of your life, whether you like it or not. And also they're moderately expensive. So this thing cost €1 billion. That was up to launch. And that's without paying the 500 people who work on it. Anyway, a brief technical aside, why are there 2 telescopes? It's interesting. I always say there are 2 telescopes, and the only people who ever ask why are there 2 telescopes are school children. It's dangerous business talking to school children. But why are there two? Well, the answer is this parallax that I mentioned we showed earlier on is when you look at a star, I did say clearly, what you see is the star appearing to move as we move relative to stars in the background. And so all you know is the difference in distance between this star and that star, but you don't have any 0 point in it. Whereas if you have two telescopes pointing at a very known angle, then some stars will be measured from one telescope, some will be measured from the other telescope. And if you know that angle, then it's a simple, trivial bit of geometry. And so you've got absolute distances. And this is the unique thing of Gaia. For the first time, it's been possible to do absolute distances to a decent number of things. Now, that wasn't supposed to happen. Never mind. The left-hand half of this slide is an historical slide. It is the slide that I presented in 2020 to get Gaia approved by the European Space Agency. And so you can see what really state-of-the-art PowerPoint looked like at that time. It was incredibly crude. But this was actually a beta-released, suitably fancy version of PowerPoint that we had access to. And that was it. But it was going to do everything. That's fine. That's what you say you're going to do if you want a very large amount of money. And this is what it's actually done. So you see, it's so far measured 2.5 trillion measurements. A truly astonishing revolution. And down the bottom here is the number of its impact on the technical astronomical community. And so there's roughly 2,000 academic papers a year. That's 3 a day being published out of Gaia. And this is a world record for everything. It's about 3 times more productive over 3 years than has been the Hubble Space Telescope over 30 years. So it's truly an astonishing achievement. It's a great contribution to knowledge, and it will continue for decades to come. Right, now, is this going to work? Oh, damn. Let's see if I can make this work. I can't make that work. That was going to show you Gaia being launched. You can live without it, a rocket launch. But the other thing you need, of course, when you've got a telescope is people to do the hard work. And so this is even more important than is the fancy technology inside Gaia. You need a lot of hardworking, dedicated people who are prepared to spend years of their lives focused on doing really smart algorithm development and software implementation to process these trillions of measurements. These are the people who are doing it. Now, is this one going to work? Yes, right. So this now is where we're at. So this is a picture of the sky in which only the brightest stars, if you try and draw 2 billion lines across a page, it just swamps it. But you can see this is how the stars are actually moving into the future, 400,000 years into the future. And so this is the first time we've actually seen all of the stars that we can see and how they're moving. So not only know where they are, we know how they're moving. You see some moving slowly, some moving fast, they're going in different directions. There's a huge amount of information in there as to what they're all doing. And at the bottom, I've pinched a piece in Galileo's writing. Galileo, of course, was locked away for claiming that the Earth moved. And he was right, of course, that yes, it does move, and in fact that is true of all of the stars and of our own sun. And so this is the information we now have, but there's more to it than that. Remember, I said Gaia produces lots and lots and lots of different pieces of information, and these we define as dimensions. And so there's about somewhere between 12 and 18 different properties of a given star are measured by Gaia. And I've listed here the interpretation of the first of them. So you can see when you start, you just got a position on the sky, then you know what's there. You observe for a bit, you've got parallax, so you know where it is, you know how far away it is. You observe a bit longer, you can watch it moving across the sky, so you know how it's orbiting around in the Milky Way. Then you measure the line of sight velocity, and that tells you how it's moving. And so you've got 3 dimensions of position and three dimensions of motion. That makes 6. And then also you've got all these other properties of the star, like its chemical properties and its age and its mass and whether or not it's got companions and so on. And so this adds up to between something like 12 and 20 dimensions. Now, people get funny about dimensions. They say, oh, well, I can understand 1, 2, 3 dimensions. That's up, down, and sidewards. And 4, well, it's time. What's 5? Well, let me explain briefly. It's actually one of the core features of the way our brains function, is that we have 5 senses. Each of these senses measures different properties of something. So when I see something, my 2 eyes provide a parallax for it. The angle between something as seen by my eyes, interpreted by my brain, tells me its distance. And when I know its distance, I know its size. And so you looking at me know roughly that I'm standing on this stage. You can guess how far away that is. You can guess that I'm a sort of normal sized person. I'm not some 3-meter tall monster that you should be frightened about. And I'm not a little tiny thing just at the end of your nose. You know, you can tell all this just by knowing. You can also watch, and you can see motion and speed and change of speed and so on. See whether things get brighter or darker. And similarly across all the other senses there. So certainly with taste, you know, how the variety of food, wine, and so on that you can taste. Smells, sound, particularly people who are interested in music, astonishingly good at recognizing all the different instruments. So all you need to have a dimension is just have 2 of these properties that aren't the same. So for example, I can have a drum. Now, the size of the drum actually affects the drum. So size is not independent of the drum, but I can change the color of a drum. It doesn't make any difference to the sound at all. And so these are separate dimensions. And so, in fact, the people who specialize in these things say that our brains work in something like 42-dimensional space. So that's why when you remember something, you not only remember all of the senses, but you remember your responses to the senses. You remember if you were happy or sad or upset, or you've got all the emotions, all the complexities, all of the context. All of this is stored in your brain in some astonishing way. So all we are trying to do here is to apply a little approximation for how our brains function to the way the universe functions. So I'll give you 4 short examples of how this works with Gaia. So the first one is and why we need so many dimensions and how we use the dimensions. So the first is a very recent Gaia discovery, just a few weeks ago. The Gaia discovered the first intermediate mass black hole in the solar system. It weighs 33 times the mass of the sun. Now, you can't see the black hole because it's black, but it has another star orbiting around it, and we can see the effect of the gravity of the black hole on the other star. And so the star was observed. So what we have from Gaia in terms of our dimensions is we have the astrometry and the spectra, that's 7 dimensions. And then I've listed all the others. So you see we have 18 different dimensions, i.e. 18 discrete, separate pieces of information about this particular system. And from that, we can, as an example of how one can deduce more about something than the fact that it actually exists. So here in the slightly complicated diagram, up the top left is the Gaia motion of the object on the sky. So you can see the red thing is what a normal star would look like. So the line across the sky is just the star moving through the Milky Way. That's the orbit. It's quite long in this case because the star's moving quite fast, but then there's the wave motion along it. That's the parallax. That's us moving, and that tells us how far away it is. But just like the case of our Earth, where there were wiggles in that line, in this case, there are big wiggles. There's this huge wiggle. And that tells us something really big and heavy is affecting the orbit of the star. And in fact, down the bottom is the calculation of what that orbit is. So here's the star that we can see, and it's moving around in this big ellipse. And here is a very heavy black hole, which we can't see, but we know must be there because we're weighing it from the orbit of this thing going around it. Now, this turns out to be a very unusual and interesting black hole. So the picture at the bottom shows you all of the known black holes in small black holes, stellar mass black holes in the Milky Way. And you see so what's here is the mass of the black hole. And along the bottom is the size, basically the size of this orbit. And all of the ones that are known in very close orbits. In fact, they're known because they're in such close orbits, the black hole is swallowing the other star and is generating X-rays, and that's how they've been discovered mostly. But they're also quite small black holes by the standards of black holes. It's 10 times the mass of the sun, which is moderately heavy, but not if you're a real serious black hole person. But over here, just showing what's different about Gaia. You see, Gaia is discovering completely different sorts of things. So it discovered 2 more of these things, rather like the ordinary ones, but just more spread out. But up here is this new thing. And so it's way, way, way more heavy than any of the others. And so that's really interesting. And why is that interesting? That's because our colleagues who study the gravitational wave universe had realized that starting 7 years ago now, when they started operating for the first time ever, that these massive black holes are actually the most common black holes. So this very complicated looking plot down the bottom basically shows the masses of the black holes, and half of them, or a third of them, are like the ones I just showed you in our Milky Way, the normal sorts of ones that weigh maybe 7 or 8 times the mass of the sun. But most of them weigh something like 30 times the mass of the sun. Now, these are the ones we had never seen one like this locally. So we knew they must exist, but we knew nothing about them, and we knew nothing about where they came from. Now we do. And we do that using 2 more of these dimensions. So the first of these dimensions doesn't matter what they are, but there's a couple of dimensions you can define that define how objects are moving in the Milky Way. And where you see a clump of things, that means this is a group of objects, stars plus a black hole in this case, that are all moving in exactly the same way in the Milky Way. There's another group there and another one there. And these 2 are known star clusters. And this I'll come back to. This is called the sausage-shaped thing. It's called sausage for a very good reason. But anyway, this immediately tells us this black hole is not a freak. It's not lone. It's got companions. And so picking 2 more dimensions, this one is basically the brightness of the star, and this is a mixture of its temperature and its chemistry. Then you find that, hey, there's a whole set of these stars, of which our black hole is just one. So it's a part of an entire family. In fact, it is a part of a star cluster which fell into the Milky Way some billions of years ago, is totally destroyed. And these stars are literally spread across the entire sky. So if you would just go out and look, you had no way of knowing that one of the stars is connected in any way at all to another one. But by the combination of these 2 dimensions and these 2 dimensions, you realize these stars all actually are the same thing. And so now we know not only do these previously completely unknown types of black holes exist probably quite commonly, we may well be able to announce a significant number more of these things at the end of next year, the next Gaia data release. But we know how old it is, we know where it formed, we know its chemical properties, and we know its age. So we now are able to understand this otherwise completely mysterious distribution of gravitational waves coming through the universe. So there's an example of how one needed all of these different dimensions to be able to learn something interesting. Now I'll give you another example. This is the history of the Milky Way itself, history of the Milky Way disks. So the text there is what I said right at the start. I don't need to repeat any of that. But on the right-hand side there is a modern version of this Tinsley diagram that was developed by Rosemary Wise and myself. So it's a Beatrice Tinsley and a Rosemary Wise and me. And what it shows is that what you expect for this dimension, this particular pattern of chemical elements versus a different chemical element pattern, is that you expect horizontal bits going down bits and then more horizontal bits. And the horizontal bits tell you that stars are forming very rapidly. If you see a bit going down, it tells you stars are forming very slowly. And if it goes horizontal, it's going even more slowly again. And it's as simple as that. And this is what we actually see on the sky, astonishingly. So here, I'll just link together. So these are these same parameters I just showed you with real stars all over them. And here's a thing in which to guide the eye. It tells you what the properties of these stars are, but you can see that there are these going down sequences and horizontal sequences, and over here's a horizontal sequence as well. And the connection to the Milky Way is that the thin disk is this stuff here, this horizontal stuff. So this tells us what we already knew, is that the stars in the thin disk are formed at a very steady, slow rate over a very long time, 7 or 8, 9 billion years. And it just every year there's another one forms. And so they're built up to be 9 billion of them. The next connection is the thick disk, this thing that was discovered in the 1980s. And this turns out to be this sequence up here, same sequence up here. And this is horizontal up here, which means this early part formed quickly. And then again, this formed over a long time. So the thick disk must have been forming stars for billions of years to have got like that. The third part is the old halo stars, and they're down here. And that's interesting, and I'll come back to that in just a moment, is why are they down here? So to summarize that stuff without too many complexities and so on, we have our 2 dimensions, and we can turn these dimensions into time, and that's pretty well what you get. So you get a sequence of time where the oldest stars are up here. So they're on this horizontal part of the Tinsley diagram. They kept forming stars for a long, long time till about here, and then suddenly they jumped in this parameter space. And then the thin disk formed, carried along down here. And so you say, what happened here then? What we can see immediately from the interpretation of this, that somebody added an awful lot of extra hydrogen into the Milky Way and reset this thing and changed. But what exactly happened? Well, we can see again from Gaia, with all of the dimensions that we have, what is going on. So it's summarized up here in the top left. And so in this Tinsley diagram again, that's older to younger, and there's time going along this way. So here's the thick disk stars, the thin disk star. So these stars here are the ones that become the precursor of the thin disk. So the galaxy didn't evolve from a thick disk into a thin disk. It evolved from a thick disk and then stopped. And then a new thing came along and set up the thin disk. And that's this. Again, this is 2 more dimensions. The details don't matter, but it describes how stars move in the Milky Way. And in this diagram, one of my colleagues, Vasily Belukharov, who frankly deserves a Nobel Prize for appallingly stupid names, decided to call this structure a sausage. You may or may not think it looks like a sausage, but anyway, that's what he called it. And so the name has caught on. And so this is a group of stars, a large number of stars, which actually form the galactic halo. And they're moving radially in and out from the galactic center. So they're not rotating the way the disks are. They're all moving in and out. And their chemical properties are these here. So these are the stars. So you can see it's coming down slowly, so that whatever the sausage was before it joined the Milky Way, it took a long time to form. And then it arrived just at this minute when the thick disk happened. And the chemical elements, the chemistry, the gas that came in with it was then converted to become available to start forming the thin disk. So this was the merger that terminated the early Milky Way, which was a disk, and it smashed into the Milky Way, puffed it up to become the thick disk, which then becomes a fossil remnant of the early Milky Way, and created a whole new Milky Way in the thin disk inside it. And all of that comes from just looking at these dimensions. Quite remarkable, really. So let's move on and do one more. Is this sort of process still going on? That merger, and remember I said right at the start that the computer simulation said there were lots and lots of these mergers going on. That's wrong. There were maybe 1 or 2, not the 20 or so that you saw. So we are learning new things that we did not know. And so the sophistication of the modeling of the evolution of the Milky Way is being rewritten by observations, and I'll come back right at the very end to how that's happening. But there's another interesting thing, and that's that this process didn't just happen once 8 or 9 billion years ago. It's still going on today. And we discovered this, myself and another different student from the thick disk in whenever it was, forget now, 1980s or 1990s, I think. Yeah, 1990s. We discovered this thing, which is a whole new galaxy, which is inside our own Milky Way and is interacting with it. And this is an old picture, so it's in black and white. But this is a modern cartoon of what we're actually seeing. And so there is a galaxy called the Sagittarius Dwarf, because it's in that constellation. There it is. We're over here looking through the Milky Way, and that's in the background. And this galaxy is torn apart, and it's left these tails and streams and shells all over the Milky Way. So the outer parts of our Milky Way is filled with these gigantic comet tail-like structures full of stars, which are the evidence that our galaxy is still evolving. And we did this in 1993. And at the time, the idea of continuing evolution of galaxies other than through major mergers was extremely contentious. And this quite interesting discovery, unfortunately, developed a US newspaper phrase, which I loathe, as the smoking gun of galaxy evolution. But anyway, that's it was the evidence that things were still interesting and still going on. And in fact, it was the combination of the discovery of the thick disk, the discovery of the Sagittarius dwarf, and some other related things, which provided the real scientific motivation to justify Gaia, when it realized that actually there were interesting things that one could learn. And so here is what Sagittarius looks like now. This is a picture again from Vasily Belukharov by a decade after we discovered it. It was possible there were then sky surveys that were digital. So you could take a digital image of the whole sky, take away all the galaxies and see where are the stars. And here is what you got. You saw the northern, this is the northern hemisphere again now. So you get these two huge streams going right across the sky. And these are the tails of the Sagittarius dwarf. And over here, yeah, that's working. You can see here's a computer calculation of what happens as something is orbiting around the Milky Way. The Milky Way is not shown in this, just to keep things simple, but you can see the cluster of stars gets shredded apart by the tides of the galaxy, and it spreads out in a great tail stream across the sky. And so as well as Sagittarius being the extreme example, extreme stream, here's another one here, and here's another one here. So there's lots of these streams up there. And this showed that one had the information to try and learn something about the Milky Way. So the next thing then, they'll say, well, we had this imaging. Gaia adds to this imaging the way things are moving. We're back to increasing the dimensionality. And up the top right, there's a rather incomprehensible looking picture that it doesn't matter. Again, it's just showing two of these dimensions with the little arrows. And the little arrows is the direction of gravity in that direction. And you see the stars in the stream, this tail of Sagittarius and the Orphan, should be just moving along that red line, but they're not. They're moving sideways. And if they're moving sideways, something has pulled them. That's the only way you can make something move differently, is to say, somebody's done that. So what's did that? Well, this is what did that. No, go back. Please work. You're not going to work. Oh, well. We'll do it on this one. Is this going to work? Yes, this one's going to work. Right. So here you see the stream of objects. And this one's got a moving Magellanic Clouds in it, you see. So here's a real modern model of how the Milky Way is working. And you can see the Magellanic Clouds orbiting around the Milky Way themselves. And it turns out the Magellanic Clouds are very, very heavy. And they're heavy enough that they pull things. And they pull, in this case, that stream off in that way. And so this pulling provides the information that you need to weigh what is going on. And so you can weigh the Magellanic Clouds and discover they're actually very heavy. Magellanic Clouds, although they look small, weigh about 1/10 as much as the whole of the Milky Way. And so the Milky Way and the Magellanic Clouds are in this tango-like dance where they're pulling around each other and moving around each other rather dramatically, such that the whole inner part of the Milky Way is swinging like a pendulum compared to the outer parts of the Milky Way, which are being stretched out by the Magellanic Clouds themselves. And so this is giving us a picture of how our own Milky Way is evolving. Now, let's go on to the one more, our last of these brief examples of multi-dimensions, and check the way gravity works. So here again is a picture of the Milky Way with the Gaia spacecraft. That's what Gaia looks like. Didn't see it before. And here's this picture of the mass and how the mass is different than the stars. The stars actually only make about 1% of the mass of the universe. The rest is something else. So how is it? So one of our ambitions, and this I'm being honest here, this is one that we failed, was to say, let's learn something about the dark matter. And so this is a state of the art of how one can measure how things move. Again, it's a rather technical diagram, two more of these dimensions. I show this one just because it's not published yet. We just worked this out with a colleague last week. But this is the state of the art for measuring how the galaxy is spinning as a function of where it is from the center. And it doesn't change its speed. Its speed is when you go, the sun is down about here somewhere. And when you go beyond the sun, the speed carries on the same. And you can do the same thing up and down and use that to measure how much is dark matter and how much is ordinary matter. And what we'd hoped to be able to do was be able to find some structure in the distribution of the dark matter. Say, is there a sort of thin layer of dark matter and then a thicker layer of dark matter and so on? Totally failed. Dark matter was completely unobliging. And so this is the state of the art as of earlier this year of how dark matter is distributed. This dark band is the how the dark matter is distributed like us. It doesn't change at all. It's just everywhere and uniform. And in fact, this was the result we first derived in 1991 with exactly the same parameters. So this is an example of how nature can prove intractable, even when you've got a beautiful experiment and a lot of data, is that nature isn't always ready to give up its secrets. So this is something for the next generation of bright young people to make a better job of than I did. Now, what comes next? Well, I remember we have these two clusters of two big galaxies with their clouds around them. There's us and there's Andromeda with its cloud. Both these clouds are moving towards each other. So that you can see in these circles here. And so the Milky Way and everything around it is moving towards the Andromeda and vice versa. They're falling in towards each other. The little bit in the middle there shows that things are complicated, interestingly, by the Large Magellanic Cloud. Now we will merge, the Milky Way will merge with the Large Magellanic Cloud, and that will create a dramatic Sagittarius-like event relatively soon, 2-3 billion years in the future. And that will be the end of the Magellanic Clouds, and it will really mess up the Milky Way. And a few billion years after that, the two clusters of galaxies will merge together to form a single one. And then the bottom is some examples of galaxies where that's happened relatively recently. So that's what we're going to turn into. But no one in our solar system, or at least no one on Earth, will be around to see that happen, because on the same timescale, our sun turns into a hot giant and the Earth will burn into a little cinder, even if it survives at all. So this is rather gloomy, but it's future. But it's interesting, of course, that although much of what I've been doing with stellar dynamics is running the clock backwards and say what happened a long time ago, we can also run it forwards. So this is not a prediction. This is a calculation. This is going to happen. So one of the few things that we're sure of is the future of our local part of the universe. And we can tell now quite robustly. And here, it's oh, good. Finally got one that worked. So here is a state of the art. Of course, now we know from the James Webb Telescope that baby galaxies, what was our thick disk long, long ago, are indeed lumpy little complicated things. And here is a state of the art of the latest computer calculations led by two of my colleagues, pictured there, showing probably what our neighborhood looked like at the time 12 or 13 billion years ago, 12 and a half anyway, billion years ago, when James Webb is seeing things like it at the early stages of their evolution. And so this is an example of how the computer simulations are going to have to go from that simple thing I showed you at the start to what comes next. Now, just to end, let me remind you, first of all, that although I have the privilege to stand here to tell you about this stuff, it takes a lot of people to run a project on this scale. And the follow-up observations, doing spectroscopy, also takes a lot of people. And I was fortunate to be able to manage that with Sophia Feltzing, who's that lady there, and this cast of incredibly talented, hardworking people. So there's a huge cast of clever astrophysicists involved in doing all this stuff. And so I will finish with my summary slide there. I don't need to read it. You can read it, but the key is that we've come a long way. We've turned our knowledge of the universe from our universe from a rather vague concept into a 18 or 20 dimensional physical structure. And right at the bottom, I'll tell you about Gaia itself. Gaia is nearly at the end of its life. 10 years old is old for a spacecraft, and so it will be terminated in terms of science operation on January the 15th. So it's got about 6 months left to go. And then it will be parked out into an orbit outside the Earth where it will last forever, longer than the Earth, actually. So after our Earth is burned up and gone, there'll still be a remnant Gaia out there for someone to find. Thank you.
What an impressive talk. Thank you very much, Gerry. We would have time to take a couple of questions. So if you would like to ask a question, I see a hand there. Dave, I'll come to you next. Can we get microphones, please? 3, 4. So we start from there.
I think it was a very good talk. So I remember at the start you showed that Gaia discovered a lot of new, bigger black holes, like larger black holes. So I was wondering, how many black holes do you think you'll discover in the next year or two? And how will that affect the energy distribution between dark matter and dark energy if we discover way more of these? Oh, and the third question is, I don't know if these were in our galaxy or these black hole discoveries, were they like around the galaxy, a Milky Way galaxy, or yeah.
Yeah, okay. So the real answer to your question is that we anticipate discovering a few dozen to maybe a few hundred more black holes because we've looked at about that fraction of the data. There's going to be a special study publishing of the black holes and Gaia's data published at the end, not until the end of next year. And we don't know the answer yet, so I can't give you a real answer. The second part is that the total mass in black holes is insignificant compared to the dark matter problem. The black holes are actually remnants of massive stars, so they're already counted in that sense of the mass that's in stars. The special thing about these massive black holes is that it seems they form only very early in the universe. So these days, plenty of black holes are still forming, but they're small ones. But it looks like early in the universe, much, much bigger ones were forming. And we found our first ever one of those that we actually know what it is. So that was the key of that observation.
Yeah, regarding what you said about the Magellanic Clouds being rather massive, was that an unusual result? And is that because of a higher dark matter content or what?
Yeah, it was, I remember when it was first presented, which was in an internal working seminar in Cambridge at the Institute, that the theorist said, that's ridiculous, you must be wrong. And then we've actually, through the same group, we found 2 other low mass or low luminosity galaxies that are also huge and massive. But the reason is that it turns out the Large Magellanic Cloud is one of these sort of super concentrated galaxies. It's actually got a really big, massive dark halo around it. And so you can even resolve out the mass, not from studies of the Magellanic Cloud itself, but from studies of its perturbation on other things. It's affecting things way, way, way much further away than it should, but in a softer way. So we can deduce quite robustly that the mass of the Magellanic Cloud is not concentrated where the stars are. It's actually got its own big extended halo. And it had been sort of expected that would have been stripped off by tides, but it hasn't been. which rather supports the idea that the Magellanic Clouds have only just arrived.
Thank you so much first for that amazing talk. I wanted to ask a question. I hope it's not too trivial, but how exactly and why exactly do our galaxies spin, and what keeps them in that uniform spin?
Whoa, that's not a trivial question.
Okay, good.
Right. Okay. So the gist of it is that when very early in the universe, there's no spin and there's no magnetic fields. Everything just sort of chaotic. But over time, you saw the structure was building up, and the structure was building up into webs and fragments and filaments. Everything that broke away from spherical symmetry almost immediately, just because they're sound waves, and sound waves are planar. So everything immediately became aligned. And once you've got that, you have therefore mass in a stream, a filament, and you take a piece here and a piece here, and they start to fall together. They'll start to orbit around each other. And the energy of that orbit is conserved. It's a law of physics called the conservation of angular momentum. And so the orbits are conserved. And as these two pieces eventually merge together, the energy gets turned into spin of the whole thing. And once spin is put in, it can only be counteracted by putting in the exact opposite and equal amount. And that's very, very hard to do. So most things end up spinning. And so it's a fundamental consequence of the asymmetry of the early universe. Not trivial in the slightest. Smart question. No.
Can you hear me now? Okay. Thank you so much for your fascinating talk. I just want to ask you about the natural lifespan of life on Earth. So suppose life persists uninterrupted for the next few billion years. When will the sun become too hot for all life on Earth, including extremophiles? And what happens to the Earth after that?
That's a very interesting question. I, in fact, had a slide on that I took out on the grounds that I'd probably run out of time. But yeah, it is something that's rapidly becoming quite accurately understood, because the sun as a star is fairly well modeled. In fact, there are people in the audience here who've won distinguished prizes for doing this. So we know a great deal about it. But so life, possibly some extremophile life is maybe a couple of 3 billion years old even, but the bulk of life on Earth is a bit less than 1 billion years. So for most of the Earth's existence, there was no what we would call life on it. Stromatolites in Western Australia are the oldest things I think we know. But so we've been around, life has been around for less than 1 billion years. As the sun evolves, it will slowly get a bit brighter and a bit hotter, and the Earth will get a bit brighter and a bit hotter. That process will be quite slow, and so it'll probably take another 2 to 2.5, maybe billion years, where conditions, there's still liquid water on the planet, at least somewhere. So some sort of life, whether we will annihilate it ourselves or not, some sort of life will still be feasible. But at that stage, the sun starts to evolve quite quickly, and it gets big. And it gets big, and therefore it's giving out a lot more energy. And so the Earth will very quickly boil dry. And so our atmosphere will boil away, all the liquid on the Earth will boil away. And eventually, as that process goes on, the surface of the Earth will get so hot the rocks will melt. And so even extremophiles will be annihilated. So that's maybe 3.5 billion years into the future. And after that, Earth is just a lava waste. There's still uncertainty as to whether or not the sun will evolve enough so that the Earth actually gets trapped inside it and falls in and melts and evaporates and is completely destroyed, or whether you'll be left with a hot, dry, cold cinder. There's a rather lovely poem by Robert Frost about life ending in fire or ice, and both are nice. Well, I think our future is both. We'll get burned to a cinder and then freeze.
Last question from there, please.
Yes, I would like to know if do the data from Gaia tell us something about for or against alternative theories for dark matter, like modified Newtonian gravity and things like that.
That's one of our key goals with Gaia, was to try and answer exactly that question. And as I hinted at the end, the answer so far has been disappointing in that we haven't discovered anything. We all were desperate to prove Einstein wrong. You know, it's one of those things everyone wants to do. It's kind of fun. But it's really too early to tell is the answer to that. Until we've got the full Gaia data set, only a third of the Gaia data have been processed far enough to be actually public and analyzed yet. So we've got a lot more to come. And there are a few interesting hints. For example, one of the tests of gravity that people have been trying to do is to look at the Newton's laws, basically, or Kepler's laws, in binary stars as if the stars get wider and wider and wider apart. And so when they're close together, it's just like the solar system. And we know that gravity works extremely well in the solar system. You know, people can send spacecraft to orbit around a moon of Jupiter to embarrassing precision. And so it works really well. But when you go to larger and larger scales, we've got no tests at all. And so it's perfectly possible that gravity isn't an inverse square law on long distances. It might be something else. And then that may, in fact, be a part of the answer for dark matter. And so one of the ways you want to test that, because the only way you can measure gravity is measure something moving. Really hard to measure stars that are far apart because they move so slowly, but Gaia can do that. And so one of the experiments that has been done badly so far, but will be able to do really well in maybe 5 years' time, is to do exactly that, to test out whether or not gravity actually behaves like an inverse square law on intermediate scales, which is 10 billion times bigger than anything we've tested so far, but 10 billion times smaller than we've tested on a universe scale. So yeah, it is one of the hopes, is that we can do that. And there's no other way known for, this is what's called weak field gravity. You know, it's easy to test a couple of neutron stars whizzing around each other or something next to a black hole or something, but that's such strong fields. We know they're okay. General relativity works there. And weak but small length scales is our solar system, and we've tested it there. But weak but long length scales, which is where the evidence for dark matter comes from, we've got no independent test at all. So that's one of our really looking forward to this type results.
Okay, so Gerry, I'll take one last question. What do you think about the rotation diagram you showed? Just beyond the 8 kiloparsec region, you see some sort of wiggle, which we have seen in VLBI parallax measurements. What does that tell you about the distribution of dark matter within galaxy?
Yeah, that's, I'll see if I can even find it. That one. Yeah, so there is a lot of structure in there, and there should be, because this is just a measurement of the rotational velocity. So Gaia's going to actually disentangle all the different velocities very accurately. But we know that the mass that we can see, i.e. the stars and so on, is not uniformly distributed. There are spiral arms. The spiral arms have a lot of mass in them. And so you would expect spiral arms to be rotating a bit faster than their neighbors. So you would expect waves and wiggles. I personally am rather surprised it's so smooth, and I'm debating with my co-author at present to what extent we've just averaged out all these wiggles and bumps, and there should be a lot more. But you're right. There are bumps and wiggles in rotation curves, and there should be, because the mass is not uniformly distributed. But whether we can determine the mass accurately enough to know whether that's also showing the dark matter is clustered is we don't know yet. The other slide I showed, or the right-hand part of that, was attempting to do that and failing.
Good. Let's thank the speaker once more. Thank you very much, Gerry. Thank you so much to all of you for attending, and that brings the public talk to an end. Thank you, everyone.